Hi, today I want to share with you Euclid's beautiful proof of the fact that there is an infinite number of primes. Before we go into the details, I want to discuss the general idea, which is a very simple idea. What Euclid actually proves is that no finite list of primes can contain all primes, because he uses all the primes in the list to show that there is a prime which wasn't included in the list. And if we include that prime in the list, well, then with the new list, and using Euclid's argument, we could also again show that there is a prime which wasn't included in the list. So we could keep adding and adding one more and one more prime forever. The conclusion is, if a list contains all primes, it must be an infinite list. A list containing an infinite number of members. Let's see the details, which in fact are very simple. We will only use very basic facts about division of integers.
Let's recall that the set of integers, positive integers, can be divided in three classes: primes, composites, and number one, which isn't considered either prime or composite. Prime numbers are those numbers that have only two divisors, which are 1 and the number itself. Composite numbers are those that have more than two divisors, as for example 20, which is a composite number. Every composite number can be factored into its prime components. Some of them might be repeated, like in this example, this is a prime, this is a prime, this is a prime. If a number is factored into its primes components, some of which might be repeated, we want to observe two basic facts. Number one, all primes in the decomposition of an integer is also a divisor of that integer. Being a factor or being a divisor is exactly the same thing. The second thing we want to remember is, or to see, is that every prime in the decomposition of a composite number is always smaller than the number itself. Keep that in mind, because we will need that in Euclid's argument. Now let's consider the last ingredient in Euclid's proof. Consider a number n which is written as the product of some factors. It doesn't matter how many, at least two. Let's put 3 for our example, and we add 1. Because of this 1, because of having added 1, now neither A, B, or C is a factor or divisor of n. For when we divide n by A or B or C, we get a remainder of 1, not a remainder of 0. Let's see an example. Number 30, we write 30 as the product of its three primes. In the prime decomposition of 30 is 2, 3, and 5. we see that 30 is divisible by 2, by 3, by 5. For example, if we divide 30 by 3, the result is 10, and there is a remainder of 0 because 3 is a divisor. But let's add 1 to this product and get the number 31. Now, neither 2, 3, or 5 is a divisor of 31. If we divide 31 by 3, the result is 10, and we have a remainder of 1, not a remainder of 0. The same thing happens if we divide 31 by 2 or by 3. This is a very important observation which we will use next in Euclid's argument. Let's now look at the core of Euclid's argument. We will show that any finite list of primes is not complete. Every time we have a finite list of primes, we can always find a new prime not contained in the list. What Euclid did is he took a finite list of primes, say like list L, which has n primes, and he proceeded to build a number we call Q, which is the product of all primes in list L without exception until the last one, and then he added 1. Well, this is a big number, obviously bigger than any of the p's, and he says Q is an integer, is a positive integer, and every positive integer is either a prime or a composite number. Let's suppose Q is a prime number. If Q were a prime number, then because it's obviously bigger than any of the primes in the list, then Q cannot be in the list, cannot be contained in the list. So this would be a new prime not contained in the list. Second possibility, consider Q were a compound number, a composite number, excuse me. Then, as every composite number, it should be the product of primes. It has a prime decomposition, a factorization in primes, into primes, and there is at least the factorization of Q in its prime factors must have at least 2 primes. Maybe both are the same, maybe it has more. Say it has n primes. Well, the fact is that every prime in the factorization of Q as a product of primes is also a divisor of Q. But no P in the list, no one of the primes in our original list can be a divisor of Q because of this construction. As we saw earlier, if we divide Q by any of the P's, we get a remainder of 1, not a remainder of 0. Well, this means that the Q's being divisors of Q and none of the P's being a divisor of Q, this means that no Q is included in this list. So again, we would have found new primes not contained in the list. This means that no finite list of primes can contain all primes. Conclusion: a list which contains all primes must be an infinite list. or said otherwise, primes are infinite in number. Thank you. I hope you enjoyed.